mentioning is that the previous chapter, right, the stuff that you're supposed to be learning for the exam next week, is that we learned how to convert groups that are already attached to aromatic rings. And so the assumption is that you know those reactions already, but now that you've learned that different groups are meta or para-directing, then changing those groups might change whether or not they're ortho, para, or meta-directing. And so in this business of designing the synthetic protocol, where you want to put specific things in specific places, textbook example is the handout you guys have for lab, right? This is where you now have to be creative, right? Because this is no longer just about regurgitation. What is that? That is that. How do you know? Because you told me, right? Like that's not what we're doing here. What we're doing here is now I'm giving you all the tools, I'm showing you all the chemical reactions, and now you've got to do synthesis. And then part of that is going to have to analyze the material and come up with a synthesis yourself. I think there's like 1 or 2 problems on that handout that ask you to do that. And I think one of them even asks you to develop a mechanism. That mechanism is actually in your notes. But you have to, be mindful that now you have the ability to change the directing effects. And that might be something that is useful to you. If, for example, you're trying to set up a synthesis, you have a group on there that you know is going to direct it to a position that you don't want it to be directed, then the alternative is if you don't have money to buy the right starting material, then just change it. So let's say, for example, you have a meta-director already sitting on your aromatic ring, but what you need to be there is an ortho-para-director. Right? So there are transformations. For example, if the group was a nitro group, and of course it will just simply put here that nitro, as is, will direct to those 2 positions in a subsequent electrophilic aromatic substitution. However, we can reduce something like that to an amine. So you can do this, for example, with zinc and hydrochloric acid, followed by an aqueous basic workup, and you can reduce that nitro group to aniline. And then once you get aniline on there, now you've effectively changed the directing, because aniline is an ortho-para director. Now, doing this, it introduces another chemical step, right? So, if you absolutely needed to have aniline, just buy it, right? But if you're in a pinch and you can't get aniline for some reason, pretty cheap, you can always do this. You introduce an additional step in your synthetic scheme, which means you might have to take a hit in yield, but it'll work. All right, let's say you had some sort of ketone. Ketones, if you remember, are also meta-directors. And one of the reactions that we learned is that you can hit this with, for example, palladium on charcoal and hydrogen, or you can use the Clemmensen reduction, which was, if you remember, the zinc mercury amalgam in the presence of hydrochloric acid and heat. And what that does, it just simply reduces off the carbonyl, puts hydrogen back on that carbonyl-carbon to generate CH2, and now you have an alkyl substituted aromatic ring, which if you go back to the notes and you're catching what we're doing here is weakly donating because it donates inductively. And then you would have effectively converted that to an ortho-para director. now that I'm on the topic, I also want to bring your attention to the reactions in the previous chapter. You know, it's expected that you know them. So I noticed that on that handout that I got from the lab, some of the aromatic rings are calling for a carboxylic acid to be on the aromatic ring directly. There's no electrophilic aromatic substitution reactions that can put a carboxylic acid on there. There are electrophilic aromatic substitution reactions, for example, Friedel-Crafts alkylation. They can put an alkyl group there. And in the previous chapter, we talked about oxidizing that, right? If you hit that with something like potassium permanganate with water, or the in situ synthesis of chromium 6, right? You will oxidize that methyl group or whatever alkyl group to the carboxylic acid. That's how you would do that. Okay. So when you start looking at that, bear in mind that some of those reactions are in the previous chapter for exam 2, for a handout that's now bringing material in for exam 3. Right, so it's building up. Right, the assumption is that you're committing to memory these things. Does anybody still need this up? All right, here's some examples of us doing the opposite. Ortho-para director. Oh, what do you know? Just the example I was talking about. So yeah, so if you haven't really looked at that lab handout that's due, you have the weekend to knock it out, because now you're armed with the rules. But this is no chemistry, right? You can get this out of the textbook if you want to. All right, so I pointed out that we can oxidize that, right? So carboxylic acid is a metal director. And so one of the ways that we could have done that was potassium permanganate. This is just one of many ways, right? There are a bunch of ways. Right, potassium permanganate, KMnO4 is a strong oxidant in the presence of water. It over-oxidizes to the carboxylic acid. It's one step before burning it. You do an acid aqueous workup in a set funnel. It's hydronium. It's the same thing. And you go from ortho-para to metadirecting. Here's toluene yet again. If you remember, NBS, if we use excess NBS, we can trigger the radical bromination. Right, that was again a reaction from the previous chapter. The radical bromination targets specifically the benzylic protons. So if you have hydrogens at the benzylic position, which this one has 3, meaning methyl, you can brominate it up to 3 times. And remember, this was a reaction that I said, remember I went over, I did this in grad school. I had to follow it for 18 hours to be able to get it to just put 1 bromine. If you let that thing go, it's, it propagates, and you can basically brominate all 3, pull off all 3 hydrogens, put 3 bromines there. And so now that you do that, this is the case where we now have strong electron withdrawing, and this effectively is now a metadirector. So there's also another set of limitations that I want to bring to your attention. It's 3 reactions that just won't work if certain groups are on there, right? Does anybody still need this up? here are two starting materials. Notice one has a ketone attached to the aromatic ring, the other has a nitro group. If you wanted to trigger a Friedel-Crafts alkylation, so what I'm setting up here is, for example, if you wanted to use this reaction to put a methyl group there, then you would get no reaction. No reaction. And so what we're pointing at here is that these are moderate to strong deactivators. If you have moderate to strong deactivators already on the aromatic ring, Friedel-Crafts alkylation won't work. You get no reaction. Another thing that you should know is that nitration will not work if an amino group is present. So if you have NH2 on that molecule, and you were trying to nitrate it, so if you remember that's sulfuric acid, nitric acid, that's not going to work. You will not get this. No reaction. Now the reason for that is because if you subject an amine group, an NH2, to sulfuric acid and nitric acid, you'll protonate that amine to the quaternary ammonium center. So it'll become NH3 instead of NH2, and then that interferes with the whole thing. So the reaction doesn't work. I will give you a little bit of advice that of these three reactions, I've been known to include something like that on the exam with potential products, and of course, one of the answers being no reaction. So this is me helping you out a little bit. Track that down before we take one more step deeper and try to consider putting three things on the ring instead of two. So yeah, so I think in the handout that you have, I think some of those problems involve putting three things on an aromatic ring. Some of them involve two. So this is where you're going to want to make sure you also pay attention to be able to do that. Does anybody still need this up? All right. Try substituted benzenes. I'm not sure if these exact examples are on your handout, but if they are, lucky you. I don't write those, somebody else writes them. Sometimes I use my notes. Sometimes people write it on their phone. Students of mine said. I was slightly appalled to see some verbatim problems from the notes in there. Just giving you the answers. All right, so look at these conditions. Br2 in the presence of iron tribromide. What is that reaction going to do? What does it add to the aromatic rings? Anybody remember? Somebody mouthly correct me, it's bromine. Yeah, single bromine. It's not the double bromine that we see in the Now, in order for us to analyze this, you see that there are 4 positions that this molecule can add to. 2 of them are the same because there's a plane of symmetry right down the middle, right? And so in order to figure out, who wins, we have to look at the groups that are already there and then ask ourselves, are these ortho or para directors? And so the first group that we analyze is the methyl group upstairs. That is an alkyl group that is weakly donating via induction. And so the methyl group directs ortho-para. So I'll write that out here, that CH3 directs ortho-para. And in this case, the para doesn't matter because there's already a nitro group at the para position. So it directs ortho-para, but it's only going to be working at the ortho position. Since the nitro group's already there, it doesn't matter. Where do the nitro groups direct? Meta, right? And so ortho to nitro, this is ortho, this would be para. This is the meta position with regards to nitro. So I'll write up here that nitro directs meta, right? And so again, it's with regards to the position of the group, right? So meta to nitro happens to overlap with the ortho positions to the methyl. And so in this case, it's really simple. They both overlap and direct to the same positions. And so that takes all the guesswork out of it. It means that we can only get one exclusive product, and that is going to be bromination at the ortho position relative to the methyl, at the meta position relative to the nitro. Right. What's the name of that product? If you use the classical name for one of the groups, what would it be? Don't forget, there's also that too. It's not just all these reactions. There's also nomenclature on top of that. You guys have your work cut out for you. Anyone give it a shot? What you got? Super close. Super close. But I'm gonna go ahead and write it. 2 bromo, 4 nitrotoluene. But you were right on the right track. That was the only difference was the position of the numbers. Yeah. 2 bromo, 4 nitrotoluene. So remember in this case, toluene is the classical name. That means this is automatically 1, 2, 3, 4. 2 bromo, 4 nitrotoluene. So here I'm just kind of putting a rule to that example, that if the directing effects of the 2 groups reinforce each other, then the reaction proceeds at that spot where they reinforce each other. nitric acid, sulfuric acid, it's a nitration reaction. See if you can predict what the product is going to be. You might have to refer to your previous page of notes to look at the ortho, para, meta directing effects of those two groups. If you have an alkyl group like methyl, what kind of director is that? Is that ortho, para, or meta? Ortho, para. Right. So methyl directs to the ortho positions. So it directs ortho, para. And of course, the para doesn't matter in this case because there's an alcohol group para to the methyl. So we only have to focus on methyl. Where do alcohol groups direct? Ortho, para, or meta? Yeah, also ortho, para. So here I'll put. So in this case, you can see that both the groups are directing opposite each other. And this is where, when we started to label strong activators and moderate activators, that's when those come into play. Of these two, which one is the strong activator? Is it the alcohol or is it the methyl group? Somebody says alcohol, anybody over here? It's the alcohol, right? It's the strong activator because it has the lone pair of electrons directly on it. It puts electrons directly in the ring, putting negative charges at the ortho-para positions. So in this case, the alcohol is the one that wins because it is the more stronger activator of the two. And so since this is a nitration reaction, we're putting the nitro group at the ortho position relative to the alcohol because it's the directing effects of the alcohol that win over the weakly donating effects of the methyl. Right, so then we can put rule number 2 here to explain that if the directing effects oppose, the more powerful activating group has the dominant influence. Try this one. What kind of director are halogens? Chlorine atom. Is it ortho-para or is it meta? Ortho-para, yeah. So if we look from the perspective of chlorine, it's directing ortho here, and para right there. What kind of director is methyl? Ortho-para or meta? Ortho-para as well. So ortho to the methyl would be there and there, and here. So So we have three positions that are reinforced in this problem. This is what the product distribution is. That's it. Can anybody guess why we don't see chlorine ortho to the right of methyl as a product? Right. What do we call that in chemistry? Steric hindrance. That's right. Because remember, you know, at the end of the day, these things have to collide in just the right geometry for the substitution to occur. And now we're talking about putting a halogen and fitting that between the methyl group and another chlorine atom when you have the two other spots that can easily collide with a higher statistical probability. And so what you find out is 3, substitution rarely occurs between two groups. There's too much steric hindrance. All right, so we don't see the formation, and maybe I should probably draw it out here just to, because I know that you'll probably pull this up one day trying to study for the exam. Like, what's the point? All right, so here, this molecule here, this is not formed. All right, so in this particular chapter, you know, for those of you who are reading ahead, the title of the chapter is Electrophilic Aromatic Substitution, but in the book and at the very end, it starts to discuss the opposite mechanism, which is nucleophilic aromatic substitution. The bad news is that for nucleophilic aromatic substitution, all the rules that you learn for electrophilic aromatic substitution, it's the opposite. So now you got to make sure that you don't confuse the two. Your saving grace is I'm only going to teach you one reaction of nucleophilic aromatic substitution, because you only have to remember that the rules are opposite for this one reaction. There's a lot more we could do, but we're not going to. I don't want to do that to you. And the textbook only introduces one reaction again. If I wanted to look outside the scope of the textbook, we could learn a lot more, but there's really no point. Electrophilic aromatic substitution, this material we're learning here, is the most useful. All right. Which is why most of the chapter is dedicated to this. Does anybody still need this up? All right, let's take a look at nucleophilic aromatic substitution. All right, so in this case, what we're going to be looking at is we're going to expose this molecule to OH minus. And so, perhaps the best way to think about this is if we're looking at OChem1, alkyl halides, exposure to a strong base, usually swaps out the halogen to generate an alcohol, right? That's basically the transformation we're trying to pull off here. The question is, whether or not it's actually going to work is dependent on the other things that are on that ring. And so when we look at nitro groups, with regards to electrophilic aromatic substitutions, nitro groups are meta-directors. But because we're looking at nucleophilic aromatic substitution, they are orthopara, which means that this nitro group is activating this position, this one and that. This is activating that position, that one and that one. This one's activating both of these and that one. And so the idea is that if in nucleophilic aromatic substitution, nitro groups are now opposite, directing orthopara, if the chlorine you're trying to swap out to generate the alcohol sits on one of those positions that are activated for, then the substitution will work. And so for something like this, you will get the substitution to work. And the product that you would get from these conditions is the alcohol at that position, which would be the para position to the nitro group downstairs and the ortho positions to the two nitros upstairs to the left and to the right. So it is activated there, and it does work. And then a molecule like this would, of course, be 2,4,6 trinitrophenol. So let me write these notes here. So I'll put that the nitro is meta-directing in electrophilic aromatic substitution, but have ortho-directing in nucleophilic substitution. And so to give you an example of a reaction that wouldn't work, this would be the substrate. All right, so trying to convert that chlorine atom to an alcohol is not going to work because the nitro group under these conditions would be orthopara directing. Now the orthopara positions for that nitro group, oops, not there, right here, and right here. All right, those are the orthopara positions with regards to the nitro. It means that the chlorine atom is not sitting at one of those positions. As a result, this reaction that you might have predicted to occur does not form. This reaction does work. The chlorine is at the para position to the nitro. This is nucleophilic aromatic substitution. So you can pull it off. That one does work. Here we have the 1,2 variant. Chlorine is at the ortho position relative to that nitro group. Substitution does work. All right? And that's the only reaction that I'm going to give you. that is going to be nucleophilic aromatic substitution. Basically, it's going to be an elimination reaction where we substitute out. So we eliminate the halogen, we substitute out for an alcohol or something like that. Kind of piggyback off of chemistry that we've learned in Chem 1. And I think that, let me see, does that wrap it up for everything in this particular chapter? Okay, I think that might be all I've got to say about that. All right, we'll see you on Tuesday. Tuesday, there's going to be a guest speaker. This is not a class you want to skip.